Okay. So, from the form of this equation, we see that these guys are independent, and this thing only depends on R. So we should be able to write an equation, an ansatz, that is, has a separation of variables. We can use that technique, and and then the two equations, the two dependents should decouple. So we say that our wave function psi, the big wave function psi, will have a factor which is phi of r, and another factor which is small psi of the vector r. So if I do this, then our Schrodinger equation decouples into two equations. One is h squared by 2 big M del squared of r, big R, and then phi of r is equal to EC phi of r. This is equation number one. And the other equation is simply minus h squared by 2 small m, del squared small psi, which is a function of r, small r, minus e squared by small r, function of r, small r. E is equal to phi of r, okay? And E total is related to EC plus E in this way, okay? So, you can show this very easily. So if I look at this equation, the first one, does the equation seem familiar? Have you seen this equation before?
The free particle equation.
It is the equation for the free particle. So its solution is very easy. So its solution is some linear combination of the following basis states at some given time. So, these are not normalizable or improper, as they're said. Okay. So, this is something we expect, because if we have a hydrogen atom, somewhere, in space, we expect it to, the whole system, the atom, the electron, and the proton, to move in a straight line, right? So, just like the Earth and the Sun, and if this is the proton and this is the electron, of course, this is a classical picture. We expect the whole system to go through life in some rectilinear fashion, right? So which is the motion of a free particle, and it'll have some total momentum p, and that is basically given by this momentum associated with the center of mass, and that is given by this, right? So this is expected. Physics works. So the interesting equation is really the equation number 2, right? So that's the interesting equation.
Sir, shouldn't there be E squared by R squared?
No, it's a potential energy, right? Not force.
I mean, in some equation I saw it was like E squared by R squared in the
It can
beginning.
only be R whole there.
Then I made a mistake there. Yeah, it's a mistake.
Yeah, I got confused. Okay, yeah.
Because we are not dealing with force, we're dealing with potential energy. All right, good, thank you. So this is the interesting equation. So, we really, there's a symmetry of this equation. Can someone tell me what is the symmetry of this equation? What does the potential depend on? Does it depend on X, Y, and Z, or some particular combination of this?
It only depends on the distance from the origin.
Okay, what kind of symmetry is this?
Spherical symmetry.
Right. So this has spherical symmetry. So meaning that if I, classically it would mean that if there's a proton and its sphere of influence around it depends only on the distance, right? So this sort of potential are called central potentials, okay? So central potentials are potentials which only depend on R, the magnitude of R, and they are related to spherical symmetry, okay? So before we solve this equation, let's choose some convenient units, okay? So let us so we know from the Bohr atom that if I give the electron in the lowest energy level the energy me to the power 4 2h bar, then the electron gets liberated from the hydrogen atom. That means this is the ionization energy. So what we're going to do is that we're going to measure our energy in units of ionization energy, okay? So that means that in the equation, we are going to, so there's a squared here, replace E by this thing. And we also know from the analysis of the Bohr atom that, the radius of the orbit of the lowest energy level is yeah, it's given by h squared by me squared. And therefore, we are going to measure distance in Bohr radius. So we are going to measure distance in Bohr radius. Okay, this is called a Bohr radius. So that means that we are going to replace r in our equation by h squared by me squared r. So if I do this, then what do I get? In the first term, we had minus h squared by 2m, and then I had del squared. But del squared is inverse of this squared, right? So I'm going to get m squared e to the power 4 divided by h to the power 4 del squared of psi. And then 1 over r gives me m e squared by h squared e squared by r of psi, and the energy gives me m a squared 2h squared e of psi. Okay. So now we can do some, cancellations. And if I do the cancellation here, the m cancels out, 2 factors of h cancels out, and then what we have is a very nice looking equation where we have minus m e to the power 4 divided by 2h squared del squared psi minus m e to the power 4 by h squared 1 over r of psi is equal to m e to the power 4 by 2h squared e of psi. So if I divide out by this factor all through, minus of this factor, I get del squared of psi, the sign flips, 2 by r, because there is no half here. And then we can bring this over to the other side, then it'll become a minus sign, but the sign flips. So we get plus e psi equals to 0. So this becomes our Schrodinger equation. Looks very nice, doesn't it? Looks very simple. So effectively, we are taking a set of units where h bar is set to 1. The electric charge squared is set to 2. And the mass, the reduced mass, is set to half. Okay? Any questions?
Why are we setting it like that? Like n goes to half? Is it like the CGS system or?
No. It's our own units. So
Oh,
this
okay.
is what we're doing. We are doing this and we are doing this. What I'm saying is that doing this is equivalent to doing this.
Oh, okay. Yeah, okay. Got it.
I mean, I can always do this, right? I can always say, okay, I'm just going to set the mass to be half, and because it's an arbitrary mass, right? It's a reduced mass. It's not a comparison of one mass with another mass, and then the electron. Yeah, so we can always do this. This is basically roughly. This means that E is square root of 2, right? So, okay, so now we are going to solve the radial equation.